My name is Bernard van der Walle, and I'm a traffic engineer at Splunk. And today I want to talk to all of you about how we use Istio at Splunk. I want to also go a bit into detail on all the trade-offs and how we decided that Istio was the right solution. So first of all, why do we even need Istio? Well, over the last years, Splunk did a migration to the cloud to be more cloud native. That's essentially refactoring, known as Splunk Cloud. And as part of this, we mainly leverage Kubernetes, AWS, and a lot of cloud native constructs. And so as part of this, we created a traffic engineering team that mainly take care of connectivity, things like VPC, multi-cloud, making sure that VPC connectivity works on a layer 3, layer 4 level, more in line with what traditional network engineers do. We also take care of DNS. We got millions of records at Splunk, both internally and externally. And yes, the issue is always DNS. We also got an application traffic management team that we refer to as ATM. That's an old networking pun for those of you that were in that field. And so that's a sub-team that is targeting layer 7 workloads, things like HTTP, gRPC, and so on. And so part of this is where we leverage Istio to do this. Okay, so let's take a step back and look at Splunk infrastructure. We got about 35 Kubernetes clusters distributed all over the world in all regions, mainly on AWS and a little bit in GCP. The way we deploy our clusters is one cluster per VPC typically, and we deploy our Kubernetes node into a private subnet, which by design means they cannot communicate to each other across VPCs. That's also why we got an internal routed subnet, and all internal connectivity is going to go through that internal routed subnet. Obviously, all external connectivity is going to take place through NLB and gateways that we deploy in some of the subnets, depending on where we want to ingest traffic from. So this is what we deployed a couple of years ago. And as we grew, we started to have more and more requirements. One of those, for compliance reasons, was to be able to enforce mutual TLS all over the cluster, both to the gateway, but also between the gateway and the pods, and between the pods themselves. So we really wanted in-transit encryption. That's probably the main use case that we were looking for. We are also an observability company, a data company, so we wanted to ingest as much data as possible for metrics, logs, and traces. We were also looking at a better way to do ingress, to be able to configure this on a couple of high-level constructs that will generate an Envoy or Nginx configuration. And finally, we wanted to be able to plug some of our authentication backends that we use at Splunk. And so what we started to do is look a little bit at what was available in the open source field, what other companies were doing. And I think like a lot of other teams or other companies, we started to try to do this ourselves by simply using an Nginx for ingress, not Nginx ingress, just Nginx with a custom controller that we built. We managed this through a bunch of OpenUST and Lua scripts that will push that configuration to Nginx. And that Nginx gateway will also do authentication and sometimes authorization. So we would basically enforce tokens into the headers. For MTLS, what we did to start with was to mandate that each workload had to load their own certificate and keys at startup and perform MTLS directly into the application themselves. Which was very manageable to start with because we didn't have that many teams to talk to. And finally, for observability, we had our own internal Splunk libraries that each application had to load. And so this was a couple of years ago, and it worked relatively well when we were still small. But as we started to scale up, we quickly saw that enforcing MTLS into the application, for example, starts to be really complex when our users start to, or service owners start to use different languages like Python, Java, Golang, etc. And each of those application libraries treat MTLS slightly differently. We had also no way to validate that MTLS was used, which was an issue for compliance. And so we started to think that the way to do this better was to shift MTLS, observability, and ingress directly to the infrastructure level, so that our users or service owners could actually concentrate on writing good code and not on managing MTLS. And this is where we went back to the drawing board, looked at what Istio Ingress could do. I picked up this screenshot from an old spreadsheet we had at Splunk to look at all the solutions. And we decided to jump all in into Istio, mainly because it checked all the boxes. To start with, we could do ingress relatively easily with Istio, with virtual services and gateways. MTLS was more or less for free as part of the mesh. It was enforced directly on the infrastructure. We had pluggable observability, meaning that we could redirect traces, logs, and metrics very easily to our backends. And finally, and this was going to bite us down the road, we decided to standardize on Mixer and use a lot of out-of-process adapters. Okay, so I want to dive a bit more into how we do some technical things. First of all, how do we install Istio? Well, we always use upstream IstioCTL to start with, and we try to define as many things as possible on the IstioCTL profile, and the community does a really good job at making this relatively easy. With this profile.yaml generated per cluster, we pass it to IstioCTL, and we get all the YAML for all the definitions of IstioD, etc., which we reload into our CI system, and we modify what we couldn't do directly into the profile. So essentially what we do is a double pass through our CI system. We use Quebec, and we codify everything into JSONnet. And at the end of the day, Quebec, our CI system, pushes it down to our clusters. How do we upgrade? Well, for us, for the major upgrades, so for example, going from 1.12 to 1.13, which we are doing right now, for this, we use the dual control plane method, which means into Istio system, we deploy both IstioDs together. What we do then is for each namespace into each of our cluster, we have an annotation use upstream, which is istio.io/rev, that will define to which control plane you want to attach. And so our gateways basically get a rolling deploy directly, but because those are atomic, right, you need to choose one version or the other, and we manage those workloads. But all the pods and nodes on the cluster, they have a mandate to be rebooted and restarted after 7 days. So we know for a fact that after 7 days, the whole cluster is migrated to the newest version. For minor versions, we upgrade in place, and that works relatively well for us. That means that we just replace IstioD with the newer minor version as a rolling upgrade. I will also say that the way we do upgrades is we always test it in dev and staging for a couple of weeks. And once we're happy with what we got, we basically push it over a week in prod. We want to be to have all of our workloads into a single version as quickly as possible. Okay, another interesting part of deployment is how we manage gateways. And this is probably one of the things we tweak the most out of IstioCTL. We always deploy, obviously, an NLB and a gateway pair together. And we deploy a lot of those pairs for multiple reasons. One of those is because we want some level of workload isolation. So typically, if we want to isolate some type of workload, we will deploy those on different NLBs. Also, depending on where we want to ingest traffic from, if it's internal or external or public. The way we do this is we define our NLB to Terraform directly, and we plug the gateways definition coming from IstioCTL that we get, and we copy-paste and adapt for each of those NLBs. One thing we do as well is we co-schedule all of our ingress gateways into ingress nodes, and each node will have multiple different type of ingress gateways. Those nodes are typically CPU heavy, and you do this because obviously as a gateway you use way more CPU than memory, but also collocating those gateways allows us to, from experience, when we see one bursty workload or gateway, typically the other ones are not. So having those collocated allow us to absorb some level of bursts more easily, while that type of gateway is scaling up horizontally. Okay, I also want to dive a bit into how we do authentication and some level of routing. As I said, unfortunately, we standardized on Mixer back in the days, on Istio policy. And we use a bunch of out-of-process adapters that we developed at Splunk. One, for example, was for authentication. One was for quota enforcement. And we also did some level of logging very specific headers. That worked really well for us, but as you all know, in Istio 1.7, this got deprecated and eventually removed from Istio. And so we had to find some shenanigans to continue to use Mixer for a little while because we couldn't get out of Mixer that quickly. And so Mixer got removed in 1.8, and thank you to the community because they gave us an escape hatch to continue to use Mixer with what they defined as the X.Z shim layer. So X.Z is that filter defined by Envoy that allows you to use that protobuf to do a sync level check on each request incoming into Envoy. And so we use Mixer by using that filter instead of the Mixer filter in Istio like it was before. And so we will continue to use Mixer until 1.10, more or less. While we continue to upgrade the mesh, we stayed up with that old version of Mixer until we could fully move out of it. And so what we ended up doing is building our own X.Z proxy, which is a central point for OZ 010 for us. And so each request coming to our gateways go to that X.Z proxy, which then dispatches it to some of our plugins, like quota, authentication, logging, etc. Specifically for logging, what we did as well is we started to build a WASM filter. And my colleague, actually, Ame, is going to go in detail into a talk on what we learned and how we operationalize a WASM filter at scale for logging. Okay, so next thing that we do is obviously we want all the data out of the mesh. So all the logs, mainly access logs, are sent to Splunk, obviously. All the data plane metrics, we aggregate them into an Istio Prometheus level of aggregation that is then sent to a cluster level Prometheus. The reason why we do that is a single level of Prometheus didn't scale up for the amount of metrics coming from Istio. And so we pre-aggregate metrics, send them to the cluster level, which is then sent to our global metric backend at Splunk that is used for alerts, etc., dashboards and everything. Finally, something that we use quite a lot at Splunk is traces. So we send all of our traces to Splunk APM, and those are very useful to debug things into this microservice world. Just a little note on this. Traces are not free, obviously. They work for us because we enforce that each workload is propagating the trace ID and the spans on the mesh. Okay, so a little bit on resource management. What we learned when we started with Istio is that we over-provisioned everything because we had a couple of outages and we got scared. And so over the last year or so, we worked a lot to reduce the consumption and the cost of Istio-related pieces. So first of all, for gateway, we typically try to set a baseline of requests for our gateways at about 60% of what we've seen historically. And we also set our HPA at 60% more or less. And this allows us to scale horizontally very quickly in case traffic picks up. What we also do is in staging and dev, we typically are fine with running one single gateway, but in prod, we try to run a minimum of 2 or 3 of them. So for sidecars, what we did is we give a low amount of requests, but a high amount of limits, and this allows very bursty traffic to go through. For very specific application, we talk to the service owners and we move up those requests by default. One thing we learned the hard way is at some point we had a really, really high memory consumption on the sidecars. And so what we ended up doing is using the sidecar CRD, which allows you essentially to divide and conquer the mesh and decide that this namespace only needs to know about that other namespace. And by doing so, you reduce the amount of configuration pushed to envoy and lower the memory. Okay, so one more thing we do is we define the service abstraction layer, which is essentially a controller to make things easy for service owners. The way it works is we quickly realize that nobody wants to configure virtual services, destination rules, gateway, etc. Those are already complex enough for us. So what we did is we try to abstract them away behind this controller, which is using an open API spec for each service, scrapes it, and then generates all of those CRDs for us. It also manages certificates, toolets encrypt, and configures DNS directly, so that it's a one-stop for getting a simple service up and running at Splunk on our cloud. Yeah, and this has been relatively successful for, let's say, 80% of the use cases. Obviously, as soon as you want to do something a bit more complex, you need to get out of this and configure your own CRDs. Okay, so one thing we had to do as well is to work on best practices, because quickly we realized that those were key to make Istio work well operationally. One of those that is not that important anymore, but in the early days of Istio, was you need to name your service ports correctly, typically with the workload type like HTTP or gRPC. The other one, as I said, is sidecar CRDs. We make heavy use of them, and we use a default one into the Istio root namespace, into Istio system. That means that by default, each namespace only get access to their own namespace with Istio. And since we got a lot of microservices that talk to each other, you need to override that one and add the other namespace you want to import configuration from. Another one is we scope internal service by default with export to your own namespace. And this, again, is with the goal to reduce the configuration being pushed to envoy on the mesh. Also, sometimes we're okay to exclude some ports and some traffic from the mesh. We do this mainly for things like health check or some level of scraping of metrics. We try to avoid headless services as much as possible. Again, this is not so much an issue today in 1.12, but back in the days, it was generating an exponentially bigger configuration per endpoint. And so we try to talk to our service owners to see how we could avoid that. And finally, for some workloads, sometimes it doesn't make sense to be on the mesh. They can directly do MTLS more efficiently themselves. And in this case, we work with them to opt them out of the mesh, and they load their certificate themselves directly to do MTLS. Okay, let's talk a bit about MTLS, which was the main reason for us to move to Istio. We still run the mesh in permissive mode, but the trade-off we do is that we monitor everything, and specifically the pass-through cluster, which is logging everything that is not MTLS enabled by default. And this allows us to very granularly talk to each service owner that doesn't use MTLS and try to make them move to the correct configuration to use MTLS. Most of the time, this is due to misconfiguration on the mesh more than anything else. With that being said, we are trying to move to strict very soon. We also deploy a bunch of validating webhooks that, with the goal of avoiding typical configuration issues. We also use them to validate that, for example, nobody is binding to a gateway that they don't have the right to bind to. It's a kind of last barrier to make sure that you don't inject or ingest traffic from internet, for example, on a host name that doesn't belong to you. Yeah, and we validate the service type load balancers outside of Istio, but also the gateway and virtual services CRDs. Okay, so one common theme for us is we spend a lot of time helping the service owners and our end users. And I'm sure all of you saw this, but 90% of the time it's due to 503s coming back from the gateway. And so what we do is we essentially managed to write a lot of runbooks, and based on the 503 flags, typically those runbooks should allow the service owners to do self-service based on those 503s. When this doesn't work, our typical workflow for debugging is to check first the Kubernetes configuration, then the Istio configuration. And if this doesn't work, we really quickly go into the envoy level. With IstioCTL, we dump the envoy configuration, try to understand what is going on. I will say that 90% of the issues, again, are due to some level of misconfiguration on Kubernetes or Istio. So what do we want to do next? Well, ideally, we are trying to move to a multi-cluster service mesh model. So today, each cluster is its own control plane, its own service mesh, which means that for policies, you need to push them individually to each API endpoint. What we really try to do is to move to a single control plane for all of our clusters, or at least a single control plane per environment. So that's one in dev, one in staging, and maybe a bunch or one ideally in prod. This will allow us to do things like workload redundancy across clusters. For example, if one workload is not available on one cluster, the mesh will allow the request to be redirected to another cluster. More things we want to do is blue-green deployments and things like zone-aware routing. So I'm going to close here with a couple of things that we learned over those couple of years operationalizing Istio. First of all is Istio makes completely sense for some requirements, but not for all use cases, right? So, and it only makes sense at a specific scale as well. I think, for example, if we didn't have that requirement for mutual TLS, we might not have ended up using Istio. Also, once you go up to scale, at this point, we got a team of 4 people working only on Istio. It makes sense to use Istio for your organization if you can get some benefit out of it. Mainly because that team of 3-4 people applies to all of your clusters, and you can very quickly scale up with this. One thing that we noted as well is we use Istio since Istio 1.3, I think, and we've seen every version is becoming incrementally better. This is very clear to us. We have seen it becoming easier to use, yes, but also it uses less resources, and it's getting easier to install, for example. One thing you need to do as well, in my opinion, if you use Istio, is you need to keep up with the community, because a lot of things move quickly. For example, that mixer deprecation, but also the speed at which Istio is getting end of life, for example, or the speed at which new features are coming in. So I think it's key to keep looking at what the community is doing if you want to use Istio. One more thing is understanding Envoy is probably the most critical thing you can do if you use Istio, because Istio is really Envoy under the hood. And as soon as we got some issues, we directly jump into debugging Envoy. We're also using a lot of Envoy filters directly to modify the running configuration of Istio, and this was really useful for us. One thing that was also a learning lesson to us is most people, or at least your service owners, your users on the mesh, they don't want to use, or they don't want to learn new CRDs, right? So what we did for us was to create that abstraction layer that allows them to try to not use them so they can actually work on what they need to work on. Last thing is, don't underestimate how much time it takes to keep the lights on. We spend, I would say, 60% of our time upgrading, helping our users, working on some security issues. Yeah, that's our day-to-day job. We only have that much time to work on actual new features, for example. And that's pretty much it. Thanks for joining this virtual session. We are obviously hiring. Come talk to me. I would love to explain more details about what we do.